Okay, so today we're going to discuss fixing your casting defects. Um, just a quick guide to get started. Tim, myself, and Jonathan will be guiding you through the presentation with some experts here. If you have any questions, post them in the chat. So just to introduce you, we have Monty. He is a manufacturing engineer for Batesville Products and has over 40 years experience in a variety of foundries. If you heard us earlier, Monty is about to take his bike out for a long weekend, starting on Friday. And then you have Ernie, who is a metallurgical engineer with extensive experience in aerospace and automotive industries. Got his engineering degree from Ohio State and MBA from St. Thomas College. And his claim to fame is engineering complex castings to a grade B X-ray and high mechanical process. And then lastly, we have Brad, who has 35 years experience. That has taken him all over the world, from Ohio to India to China. And in 2016, he created the Porosity Solutions company. All right, now that you have a brief introduction of everyone, let's get started.
Rachel, appreciate it. First and foremost, I think in previous discussions I had mentioned, with that wealth of knowledge across these three gentlemen here, I'm going to look like an idiot today, I think. All the experience that they have there, I'm very small over here at the 10-year experience versus the 35 to 40 year there. So, definitely a wealth of knowledge. So excited to have the guests that we do today. Feel free, as Rachel mentioned, if you guys do have questions, to pose them to Jonathan and Rachel, and we'll try to get them answered live today. Anything that we can't answer live today, we'll make sure that we follow up afterwards. If you guys do have any questions, or if anything wasn't able to get an answer on the webinar today, we'll make sure we get that done. So first slide here is really showing a number of the casting defects that you could see across different types of casting processes. And really just wanted to put this here for ideas that, everybody can kind of reference or look at when they're, looking at castings in-house, or maybe looking at a possible issue that they're running into. But today, mainly the 6 things that we want to go over and talk about with the panel we have here are really these 6 porosity defects. So first and foremost, the surface porosity, we have reaction porosity, gas holes, oxide related porosity, any kind of shrinkage or hydrogen gas porosity. So with that, let's jump in here. So on surface porosity, Brad, so what are we talking about here when we're talking about surface porosity?
This slide is showing, customers, first of all, customers call almost all defects porosity.
Yeah.
So what we're looking at here is some blisters on this slide where it's flaked away. And this is a little different than reaction porosity, which we'll go into detail, but dirt in the sand mold. Maybe Ernie can expand on that a little bit.
Yes, surface porosity. Yes, surface porosity primarily just lays on the surface. In sand molds, it tends to be dirt if it's in the cope half of the mold, and then it tends to be, or if it's in the drag half of the mold, then it tends to be a dross if it's in the cope half of the mold.
Ernie brings up a good point when you're looking at porosity, to look at the location, and that will help you determine what kind of porosity it is.
Okay, so there's a couple different examples here, and I think Ernie and Brad, you guys kind of hit on it a little bit. When you're talking, dross and in the sand molds, but even blisters you could see in die casting or permanent mold, oxides you could see across almost every casting. Is there a typical surface porosity you're seeing, Monty, when we're looking at castings, or is it really across the board different every time?
In our case here, we don't really see too many surface, other than maybe gas once in a while.
Okay.
But that's
Just one more thing on this slide. the oxides show up as surface porosity, but they're not really porosity until you machine the part. The oxides will be hard and they'll tend to tear. So when you're machining, if you're having a lot of rejects on the surface and machining, those typically are oxides. They'll pull out during the machining process.
Okay.
Yeah, characteristically, those will often have a stringer attached to them also.
Okay. So the next one we'll talk about here would be the reaction porosity. And I think this was, we actually had kind of a quick conversation before we had gotten on. We have a part here, and Monty, I don't know if you want to talk a little bit more about that part, and what we're trying to do is not necessarily on the casting side, but it's on the sand core side.
Yes, we have a problem with sand sticking into the casting and not coming out. Even in heat treat, it's not coming out. So we're trying to use a coating on the core and see if that helps at all. I have a choice between water base and alcohol. We don't have an oven to cure the water base, so we are going into the alcohol and burn it off.
And I think that's when Brad hopped in, and Brad called it what?
Reaction porosity, absolutely.
There you go.
And the reason Monty said, you have to dry it. So if you put a mold coating on and you cast that wet, there's going to be a reaction between the molten aluminum and the mold surface.
The most critical thing is it'll be just very close to the mold or to the core surface. You won't see the porosity typically anywhere else in the part or adjacent to the part, just very close to the core. If you have a round core, it'll often show up as just like a pattern of holes all kind of outlining the core. But very much surface related.
It's interesting because on this casting shown here that you have a reaction with the mold, but on a sand core or on the core, you have a reaction with the core that's going to show up internal, on the internal surfaces of the casting. So it's critical to, as Ernie said, it's surface related. If you were to take a cross section through, you're only going to see it, very close to the surface. It's not going to be internal.
So
typically it's a finite type of porosity. It doesn't leak or anything. It's just what you see is what you have.
Okay. So the next porosity that we are talking about here would be the gas hole porosity. So Ernie, explain to me what the difference between the gas hole versus the surface porosity we just talked about, or the reaction porosity we just talked about is.
Gas holes are almost always internal. They're almost always round in appearance, and usually they're very localized. They're usually based on metal turbulence, either something coming down the down sprue or something leaking in at some point in the gating system. They're almost always related to some form of metal turbulence.
Okay. In Monty, I think you had mentioned too. So you said in our process here, typically this may be the most common, if any, process that we'll see.
Depending on how fast the tilt pour is operating, it may hit bottom, cause turbulence in the bottom end before it goes into the casting.
So is that why you pay very close attention to tilt times?
Yes.
And pour rates and the turbulence, yes, as Ernie was just mentioning. Okay, so instead of really making this a one size fits all, it sounds like it becomes very custom to the part.
It is. It's individual.
Okay. So how would somebody anybody that's on today or anybody that has that type of question, is there a science to helping get that gas out? Is that slowing down the tilt pour? Is that on the molten metal side?
A lot of it's to do with the runners and the gating.
Okay. Slowing
the velocity down or speeding it up depending on what you want.
Okay. Very interesting.
They used to use the term as trying to get like a lamellar flow. You don't want the metal tumbling out of the bottom of your gating system. You want it flowing out of the gating system. and that's maybe more not a technical term. It's just if you picture what you're trying to do, you're trying to avoid that tumbling and the chaos at the bottom of your sprue. You want it to come out of there in a smooth manner.
Sure, and I think it could go the opposite way too, right? You could go too slow and not get your casting to fill out. So there's definitely a sweet spot in the middle ground there that is ultimately the area we want to achieve, so that we're eliminating any of the gas
Especially
holes.
in permanent mold.
Yep. But not necessarily making sure that the part doesn't fill out, because you still want to make the part the way the customer is requiring it. So great. So Ernie, can you talk about what's going on a little bit in this picture here?
I think Brad, you'll bring you in on this too, but also I think just the key point is, again, it's local and you can see round edges on it. Most gas holes, again, are tend to be round. Brad, when you look at the microstructures and stuff, you may want to show what you see.
Yeah, this is just a picture in the microstructure, as you know, as opposed to a cut section looking at the holes, or an X-ray that we just saw on the last slide. And it looks very, very similar to hydrogen porosity, which we'll talk about later. But the key is, as Ernie just said, it's localized. It's going to be in the area where the turbulence is. If it's hydrogen, it's something in a melt, and it's going to be throughout the whole casting. So if you're not going to be able to fix an issue unless you can identify it. So that's why we're talking about the different types of porosity and the different characteristics.
So that kind of a big question here with the oxide inclusion. So there's a difference. This is still caused by turbulence, but there's definitely a difference in the oxide inclusions versus what we just looked at. Explain that a little bit, Brad.
Well, the turbulence is actually mixing the oxide, the oxide that form on the molten aluminum surface. All molten aluminum has an oxide layer. So if that layer gets folded in, it creates this oxide, and that's what you're seeing here. And oxide itself is really not porosity, but it changes the solidification in that area, so it doesn't completely fill out, and that's why you see the porosity kind of intertwined amongst the oxides there.
This is what we talked about earlier too. It's not typically a well-defined porosity as much as you see the stringers. If you look at the picture on the far right, even at a macro level, like if you're machining it, a lot of times you'll see a little bit of porosity that you've picked out as you machine it, but you'll see a tail or a stringer tending to come out from behind it. And that's a good picture of what we talk about, having a stringer attached to it.
In Monty, something like this, like the oxide inclusions, you were stating typically this isn't anything you would see in permanent mold, and is that because of the gradual tilt pour that really solves this out of it?
The time it takes, and also you don't get the turbulence normally like you do dumping down and down sprue, or even it has oxygen also has a little bit to play in it as well.
Okay.
Yeah.
So is it something you can see in die casting?
I'm ready to say that, yes.
Okay.
You can, yeah.
But is it most common then in like a sand casting atmosphere?
Not necessarily. We had a vacuum cast. Anything that you need to fill the metal fairly fast, we were filling blades that were 10 thousandths thick, and so if you picture that, I mean, that's going to freeze off very quickly. So we have to fill it very fast, but without turbulence, and we were riding right on that edge. A die cast is squirting the metal in there very quickly. You can get oxides in the die cast. The permanent mold, if you have a good smooth fill, if you're pouring in a sand casting and you're pouring too high, or your gating's not correct and you're filling too fast, you can get the oxide. So it can happen in anything, but the faster that you fill, the more prone you're going to be to having them.
Brad, you can also the oxide trapped in the metal, introducing it to the mold.
Absolutely.
If you look at that middle slide, you can see an oxide trap behind the filter. That oxide was actually generated in the furnace, or the melting furnace. So it's just not a result of your gating. It can be entrained in your melt.
So if you're using a lot of scrap, and particularly if you're remelting gating, because gating will have oxides on it, you can introduce those oxides right into the melt, as Ernie says, and they're going to stay in there unless you have some way to filter them out.
Okay. Ernie, can you talk a little bit about what this picture is showing here?
This is just a magnesium oxide inclusion that formed at the chill face. Is that correct, Brad? I think.
Yes, absolutely.
And one of the unusual things about these types is it actually had a skim over it, almost like a flake that you could pick up to see what was underneath of it. Again, just an oxide that's filmed. This one is Brad, is this related to the two mold faces, two metal interfaces coming together?
No, I don't think so, Ernie. I mean, it's probably more related to not when you're adding more mag to your melt, of not distributing that evenly. So you have an area that's enriched magnesium.
Yeah.
And go ahead.
This would go to the point if you're making an alloy addition, you have to make sure that you get it plunged and thoroughly distributed through the melt.
So the oxygen not only attaches to the aluminum to form the aluminum oxides, which we saw on the previous slide, it will combine with the magnesium to create a magnesium oxide.
Hey, Monty, we have a question. David wants to know, it seems like the speed of the pour, fast or slow, is important. How is the pour time controlled?
Pour time is set up with the a timer on the press itself, as far as how many seconds it takes to tip.
So that'd be on the permanent mold side.
Yeah. As far as gating goes on a sand casting or anything like that, normally to control it, you choke it or open it up depending on how fast you want to go.
Absolutely. As Monty said, the gating controls the speed on a sand cast.
Yes.
Most of the aluminum systems are what they call unpressurized, where you don't want the metal with a lot of force going into the casting. You want it to be choked off somewhere before it starts to enter the casting, so the metal is free to flow into it rather than rush into it.
We've also had points where you choke it too much and spray the metal in and erode the core or the other side of the casting.
It doesn't sound like something you want.
Nope. Spraying is never good.
Well, that's that local oxides or dross you see on the surface when you do that.
Yes, yes.
Great. So some good conversation there. So yeah, Jonathan, I appreciate the question, and I'll continue to encourage if people do have questions while we're live, make sure you're popping them in the chat there and we'll get them answered. So the next one we want to talk about here would be shrinkage porosity. And I think, Brad mentioned it earlier on. A lot of the customers or prospects consider everything porosity, or a lot of different things porosity. Shrinkage isn't necessarily in that category, is it?
I don't think it is. It's more in the category of how your rise ring and gating is, depending on if your risers are working the way they should be. You shouldn't get too much shrink, but you still can. It depends.
Okay.
Depends a lot on the shape of the casting, and I'll let Ernie get in a little detail on this.
It could be a long range casting.
But first, shrink is a solidification defect, and the only way to fix it is to freeze the metal, or to feed it, freeze it or feed it. So you have to get the metal there quicker, or you have to chill it faster. I'll let Ernie go into detail, because this is a very common problem, particularly on complicated or complex castings.
Shrinkage porosity is first thing is it tends to be localized. Second thing, it's kind of misleading, because you can machine across the surface with shrinkage porosity and it'll look good, but it'll actually seep or leak, because if you look at that picture on the right, you can see how the interstices are all connected. And so that's the form it takes. So you may have a part that looks very good. If you put it under pressure, you'll actually see it seeping a little bit. The picture on the left, it's hard to see, but if you look at the bottom, that's a solid. Aluminum solidifies dendritically. And what happens is, even if you have your gradient, your progressive solidification like you wanted it, you can get little areas trapped between those dendrites as they form. And if you look down towards the bottom where that solid interface is, you can see some areas where the big shrinkage is up towards the top of that slide. But down towards the bottom, you can see where there's some very minor areas that have been trapped as those dendrites have formed. You just haven't been quite able to get metal to them. And that what you see in that kind of the mid-lower part of that slide on the left is, and when you look at an actual microstructure, is what you see there on the right. And again, it's those interstices connected. It tends to be local. It's definitely related to feeding the part. And like I say, one of the characteristics is it just tends to have a very slow seep or leakage in it.
Commonly happens, well, a couple of places. One is the last place to solidify. It'll happen a lot towards the gate, towards the towards the gating, but the also it happens between thick and thin surfaces, thick and thin walls of the casting.
Mhm.
You may see it not too far from the riser where the riser just didn't have enough quite to get it all the way there. And you'll see an area that may show sponge shrinkage like that.
Where your connection neck down, whatever you want to call it, right at the connector at the casting to the riser is normally the spot that freezes off, and then you end up with shrink there as well.
Yeah, correct. Sometimes you create a little hot spot right in front of that riser. It just doesn't quite feed.
The picture on the left looks like
Oh,
a
sorry.
beautiful piece of artwork, but I'm not sure you want that in a casting.
Well, there's an interesting story about that. I actually found that in a McDonald's in Alaska.
Oh, really?
And what it is, if you look at it, the bottom, it's water freezing. If you look at the bottom, it's water freezing, and then you can see the dendritic starting to come out from that, and it continues to feed. It's much like what you see on a glass when a frost freezes. That's exactly how aluminum solidifies. You see it start, you see the dendritic arms start to shoot out from that. That's the same way aluminum solidifies.
So it is a piece of artwork. Great. I want to.
It was.
Where do we go?
Hey, Tim, real quick before you move on, we had a question about risers. Is it more effective to increase the height of the riser or the diameter of the riser?
That's a great question. Monty's got a lot of experience on a recent product with that. So let's toss it. So the question was, is it better to have the length of the riser bigger or the riser itself bigger? So what helps feed your casting? A bigger, a longer riser or a thicker riser?
I guess that depends on the casting shape.
Very good answer. Yeah, it's a great question because again, every product, there's different processes like the sand casting, die casting, permanent mold. We even talked a little bit about the vacuum process, and in every process is going to have some different needs for them.
Yeah.
But when you get into products, every product's going to have a different way you're going to need to fill different areas that need to fill different critical areas.
Risers are never the same. They're always built for a particular job.
It depends on the issue, because the higher the taller the riser, the more pressure you're going to have on that metal filling. So you're going to be able to pressurize that casting. So if your more pressure of the molten aluminum is going to fix your issue, you go higher. If you need to feed it faster, then the wider riser is going to help you there. So it depends exactly on the type of casting, as Monty said.
Yeah, actually, it really depends on the casting section you're attaching it to. If you got a 1/2-inch wall and you're going to put a 4-inch riser on top of it, it does absolutely no good at all, because as soon as the wall stops feeding, the riser stops feeding. You got to remember everything. Yeah, everything in the riser has to feed through the part. So you got to look what it's attached to. As soon as the casting solidifies, the riser is done.
And risers aren't necessarily always, just a cone or a cylindrical shape. I mean, they can be.
It can be square. It could be round. It could be egg shape, whatever. It really doesn't matter. It depends on what you're feeding.
Great. Hey, Ernie, what do we have going on here?
Well, this is an example. This goes back to that elongated porosity or the shrinkage porosity where you're talking about. And as Brad says, this is a case where you can see the penetrant inspection on both sides of the part when they penetrant inspected. So visually, the part looked very good under just white light. But when you put a penetrant inspection on it, you could actually see how those interstices connected. And you showed porosity, very fine porosity on both sides of it, and it leaked through that passageway.
It was an oil passage, and we sectioned that casting long ways because it was leaking. Oil was leaking out of the side of the casting through the casting, and so penetrant tested it, said, okay, it's leaking here. Let's section through. But we're going to see shrink porosity, and we did. You see it on both sides.
So this is a little bit, I actually might jump ahead real quick and come back to this slide. So is this kind of a more detailed example too of what you were just talking about where, you can do some of that liquid pen there and put some of that material in here to see some of that shrinkage porosity?
Yeah, just for anybody out who's not quite familiar with what penetrant is, a very layman's term, if you picture just a penetrating oil, pick WD-40 and add a fluorescent dye to it. It'll carry itself into the parts. You wash the oil off and the penetrant dye remains. And so you can see it through a capillary action, it goes into very small porosity. So that's what you see in that slide. Then an X-ray grade thing here, when you're looking at, again, this is elongated porosity. And two things to look at. If you look at like the grade D slide on there, one of the things that differentiates shrinkage porosity is it tends to appear elongated. If you look so closely at that slide, instead of having round porosity, it tends to be an elongated porosity, again, because it's trapped in between those interstices on the, like we saw on the dendritic. And these would just be different X-ray grades of when you were grading porosity, elongated porosity. These would just be levels that progress from good to worse. You see the shadowy effect in the grade D slide. That's which actually go into something called sponge porosity a little bit, which is just it's kind of a step below a shrinkage cavity, and it's a little bit worse than the isolated elongated porosity like we see there.
So I'm going to step back real quick, wrong way, and talk about the shrink cavity, which you had just mentioned a little bit there, Ernie. But are we seeing shrink? Is the shrink cavity more specific than what you'd see in a consistency where you're looking at the elongated side of things? So on the elongated, it looked like there were a bunch of those little porosity holes or shrinkage holes versus what you're seeing here in the shrink.
It's a progression as you start to feed through the risers and stuff, depending on how well you did it. Like you said, the shrinkage, the elongated shrinkage is your first near miss. Then it goes to the sponge shrinkage, which means you missed your feeding range by just a little bit more. And then the one where you just don't quite have it yet goes to a shrinkage cavity.
Okay.
And so it's a progression of shrinkage defects, basically, with elongated, the least severe, then into the sponge shrinkage, and then into the shrinkage cavity. And these slides here happen to be shrinkage cavity. And so you've actually failed to get metal into to that portion of the part, and it's actually isolated a cavity. Again, if you look at that grade D slide, you see that dark area all around the cavity. That's back to more what they would call sponge shrinkage.
Thanks, Ernie. So the next one would be the hydrogen gas porosity. So what we're looking at here is really the how much gas are you seeing within the part? And this is something you kind of hit on earlier, Monty. Is this, or what tends to cause this, and what are you seeing in castings when it comes to the gas porosity?
Most of the time when I see hydrogen gas, it's coming out, coming out of the furnace, going into the casting. Most of the time it's in the furnace, if it's not degassed properly, or might be imperfection in the metal itself.
Okay. So that I think that kind of went into what you were talking about earlier, Brad, and you were mentioning that, if you're putting not necessarily bad metal, but if you're putting back in remelt or scrap metal, does that tend to drive the hydrogen gas porosity that we're talking about here?
That will drive your oxides, and if you had a high hydrogen content in your castings, yes, it could. But this is more of a reaction with the molten aluminum to the air. So hydrogen in the air it has an affinity for the aluminum. It's going to it'd rather be in aluminum than in the air. All molten aluminum has hydrogen in it. And the issue, go ahead.
So absolutely different than what you were talking about earlier from the oxide shrinkage or porosity that we were talking about versus the hydrogen gas porosity.
That's correct. So all hydrogen, all molten aluminum is going to have hydrogen. And so the issue is how much can you stand when you cast? Do you want hydrogen or porosity-free castings? And if so, you need to degas. And the only way to get rid of the hydrogen in the molten aluminum is to degas.
Okay.
Go ahead. The next slide. So hydrogen. Go ahead.
Brad, you may want to go back one slide and talk about the temperature relationship since it shows on that slide.
Okay.
Go back one slide. There, Brad, pick that up.
The reaction that hydrogen has with the molten aluminum, there's two main factors, and one is the moisture in the air. So the higher the humidity, the faster the hydrogen is going to go in, and number two is the metal temperature. So at 1400 degrees, over 1400 degrees, I think it's every 100 or 150 degrees after that, the rate that the hydrogen enters doubles. So it doubles. And so typically that's why you want to cast, your molten metal temperature, your casting temperature to be, 1375, 1400 at the very top, if all possible. Because the higher the metal temp, or the higher the metal temperature and the more moisture in the air, the more hydrogen that goes into the melt.
Yeah, and then before you go on, the little top line on your slide there is the key thing. The hydrogen is soluble in molten aluminum, but it's not in solid aluminum. So as the aluminum solidifies, that gas comes out and forms porosity in your casting.
Yep. So now this shows as I said, the hydrogen is throughout the melt. So it's going to be everywhere in the casting. And if you were to take a microstructure and look at it like one of the previous slide of the gas hole, it's going to look very similar at that 200x or 100x. It's going to be smooth. It's going to be rounded. But the difference is it's going to be everywhere. It's not going to be localized. So it's very easy to tell if you have a hydrogen porosity issue. It's not going to be on the surface. Your surface is going to look fine. But if you machine the part, you're going to see the holes. If you cut the part section it as it's shown here, you're going to see the holes throughout.
So, this definitely sounds like something that's very important if a customer is designing a product that needs to be structurally sound. If it's not something you're going to see on the surface, doing that mechanical test or tensile strength, really showing, the ultimately the internal strength of that casting rather than.
You probably won't see it unless you machine it or grind it or something like that and break the surface.
Okay.
Got a couple more questions, Tim, before we move on. First, what is your thoughts about adding gas to the metal to combat shrinkage?
What kind of gas?
So say that again, adding gas to the metal?
Yeah, what's your thought about adding gas to the metal to combat shrinkage?
Like we do when we throw a 2x4 in the aluminum. We're adding gas.
Yes.
Yeah, I call that organic modification. This goes to what Brad is talking about, that there's always gas in a casting. It's not necessarily to your advantage to have it gas free all the time. It's a match up to what your customer requirements is, to what the casting is, and it's an economic matchup. It depends on, again, where you want to go with your part. Adding gas in, what it does is it takes up some of that shrinkage porosity we talked about. Mm-hmm. It takes up some of that volume expansion of that, and it gives it will make your part. it spreads that out. So you tend not to congregate your shrinkage and stuff. And that's basically what it does. Very common practice. And Brad will talk a little bit later here about why it's so important to identify the gas level you have and then know the gas level you want, because it may be two different things. It's just not always get it all out.
If the criteria is a good surface finish, then the internal doesn't matter, right? So the hydrogen porosity is never on the surface. So you know, and shrink can be, and shrink typically is. So if you want to, you know, eliminate your shrink, or you have a corner that needs to be good where you don't need shrink in the corner of the casting, sometimes gas level is okay.
It's pretty much a standard practice in permanent mold, depending on certain parts to add some gas in some form or another. I've seen potatoes, I've seen 2x4s, I've seen pretty much everything used to add a little gas into the part.
And some customers will state it right on the drawing what they want.
Yeah, and I think it goes back to the testing too. I mean, if a customer is designing for a you know, mechanically sound product that needs to withhold certain tensile strength, you know, you try to eliminate from some of this hydrogen gas porosity, but I think you hit the nail on the head there, guys, with you know, there's medical food industry where it's very important that nothing's getting into it. Right. So from the surface perspective, very important that it's high end finish on the surface, whereas, you know, internally it may not be, you know, as important. So good discussion.
Yep.
Yeah, that second question was, how much does chemistry impact the hydrogen levels?
Not too much. The chemistry does not affect it too much. It does some. You know, a lot of the foundries will be running okay. They'll be running a 356 and then maybe 319, and sometimes the 356 will pick up gas a little quicker. It depends on it's basically related to the fluidity of the metal. So if you look in your book, the fluidity of the different alloys can be a little different, you know, but it's not that much. It doesn't make a huge difference. If you're thinking, okay, the spec on my 356 is this for mag and so on, and you're at the lower end of the range or the upper end of the range in those specs, it won't make a difference.
It has very little effect on the, I agree with Brad on the hydrogen porosity. Pushing your chemistries in some different directions will have an effect on your shrinkage porosity, possibly, you know, especially on your levels of titanium, things like that. But especially, like I say, not so much on hydrogen, but shrinkage porosity, your chemistry levels will have an impact.
Thanks for the question. Brad, you want to talk a little bit about what's going on here?
Yeah. The jump back one slide real quick, and
Sure.
I'll just touch on that for a second. You show the so this is just the degassing and degassing media. Typically argon and nitrogen. You know, chlorine is still used some, but very little. There's a combination of a gas. It's SF6. It's sulfur hexafluoride that's used, but typically it's argon and nitrogen, and all it does is it attaches to the argon and nitrogen attached to the hydrogen and float it to the top. When the hydrogen reaches the surface, it actually burns off. So if you have a lot of hydrogen, you actually see flames on the surface. The chlorine and the SF6 actually chemically combine with the hydrogen but bring it to the top in the same manner. Okay, next slide then. This is just this is a study that I did where I was measuring the hydrogen content with a meter, actually in the molten aluminum, and then I was running trials with reduced pressure test, looking at the specific gravity of the samples, and so this just shows us for our process at the end we could run in that yellow range, and if it fell below the bottom of that yellow range on the left, then, you know, if it was 2.5, if it was 2.59 or lower, then we'd have to degas again, or we would have porosity in our casting. But the key here is you know, if you did need, you know, if you want a porosity-free casting, you just define the level, you just determine. Typically on a 356, if you have a 2.59 specific gravity where you measure your reduced pressure test sample, a sample solidified under vacuum, if it's 2.59 or higher, you're not going to have hydrogen porosity in your casting. It's lower than that, you can, and the farther lower it gets, the more hydrogen that will be in there. But if you wanted hydrogen gas in the casting, so to reduce that shrink, as we talked about earlier, you might say, okay, I need to run in a range of 2.46 to 2.50. And that's where using specific gravity is the best way to evaluate the amount of hydrogen that's in your molten aluminum. You know, a lot of people will slice the section and then they compare it to a chart, but three of us can look at that sample one, come up with three different numbers. And this is exact. It takes like 15 seconds, you know, you put it in, you weigh it in air, you weigh it in water, and a calculation's made and gives you your specific gravities. So that's what this chart's all about here.
Yeah, the advantage is you can actually write your procedures to have a numerical value into it instead of just a visual reference.
I think that's key, Ernie. We talked about a lot of different stuff, and you know, you kind of hit me a softball here. You know, giving me some thoughts here when we go into the troubleshooting, and we talked about it a lot. And I think, you know, the specifics. So you know, we talked about different gates and the way that flows in, the different size of risers. It all comes back to, it's very specific to the individual part you're looking at.
Mhm.
You know, a lot of the stuff that's almost everything that's being done in the casting process is not your off the shelf type of unit. You know, no matter what type of casting process you're using. So, you know, these are some lists, and a lot of the stuff we had mentioned over and over and over again in this conversation today, but a lot of the different areas to continue to look at and really focus on as you develop out what is a good casting to you. Because, you know, even on the hydrogen porosity side, if you have it internal, is that fine for your product? You know, what's the end product need and use? So this is a good troubleshooting tips list to look at as you work through designing. And then the last thing was really the directional solidification here as well. You know, so again, when we're talking about risers, we're talking about gates. Really, how do you develop out your casting? You know, what's important, what, you know, is surface finish important, is the tensile strength important? You know, are you okay with some porosity and not all porosity? You know, so really a good instructional sheet to look at here. So, you know, really appreciate everybody's conversation today. Brad and Ernie here actually have, you know, again, an extensive background along with Monty. You know, so we really encourage reaching out to both of these groups here. Whether, you know, you go directly to Ernie and Brad here through the Foundry Way, or reach out to Monty here at Batesville Products. There's a very expansive expertise over years of developing this stuff out, and hopefully you picked up some of that today, because a lot of this, you know, even being 10 years in the industry, I've learned a lot today from talking to you guys. So, you know, again, if there are any last minute questions, we can answer them now. But we'll send out this PowerPoint to everybody as well as the recording. There are typically some short videos that will come out as well. So keep your eyes out. But make sure you check out, you know, not only the foundryway.com for, you know, the casting course that Ernie and Brad here provide, but there's also some articles, podcasts and guides that are out there, you know, that hopefully help answer your questions. But again, you know, feel free to reach out to these guys. They're experts in the industry, to say the very least. So with that, appreciate everybody joining today, and thanks again to our guests.
Yeah, Tim, we did have two more questions. If you want to knock those off before we close up here, that'd be great.
Absolutely.
First one is, we have porosity holes on ingate of casting after grinding. Would that be a gas if it is on the surface of the part, or something else?
And the end gates.
It was on the in-gate.
Yeah, it says they have porosity holes on the ingate of the casting after grinding.
If it's in, it's hard to say. Again, this goes back to location. If it's on the cut surface, it's probably a shrinkage porosity. If it's right in front of the in-gate where it's come to the top of the part, it's probably a dross type of defect.
It's hard to tell without actually looking at the, we would take the porosity, you look at it under the scope, and microstructurally they have, they look different. So we can typically identify what type of porosity it is, but you can't tell. That's something we go through in our class, but without seeing the porosity, it's hard to tell exactly.
Sure, and maybe they can get in contact with you. It was kind of continuing on to say they know, you said gas is usually internal and not on the surface. They figured, it was always figured it was gas. So they were kind of just trying to figure out which way it was. So maybe it's best to kind of take a look at the part.
Yeah, it could be gas. It could be shrinkage. Could be some trapped dross, as Ernie said. It really have to look at it under the scope and in context with the casting.
Sounds good. Thank you.
All right. Well, I appreciate everybody hopping on today. And again, special thanks to our guests joining. Again, highly encourage hopping on the website, reaching out to these guys. Any additional questions, we'd be happy to answer offline. Thanks again.
Thank you.
Thank you.